Okay, with that we have come to the end of the material for this particular course, right? So let's quickly sort of recap what it was all about, and hopefully it makes sense at the end of the day, right? So roughly speaking, what we have focused on is hardware integration, meaning that how do I take a custom piece of hardware that I have got? We use the timer as our sort of running example through most of the system, and integrate that into the Linux kernel so that I can talk to it from Linux. We started off by seeing how memory mapped I/O is sort of the core idea. We have the Axi-Lite interfaces that are present on the digital side, the design side of things. But then there is the device tree, which allows the kernel to know what kind of devices are attached, and the platform drivers that we can then use in order to actually communicate with these systems, right? Co-simulation with Verilator and Renode can be a very powerful sort of environment for testing and debugging, right? It basically allows us to parallelize our processes, meaning that our driver development can start at the same time as what we are doing with the digital design itself, the RTL development, right? Now, variations of this are what are used in industry. Not all companies are going to use Verilator or Renode. They would have their own mechanisms whereby they would have either some kind of simulation or a higher level emulation or possibly an FPGA accelerated emulation, various different ways by which they sort of streamline these processes of developing the hardware as well as the drivers. Now, in the later weeks, we talked about slightly more advanced driver development, in particular interrupts, DMAs, the problems with memory management, and so on, right? And finally, what we looked at was system architecture level problems, which you are likely to face when you are actually dealing with building or designing a full-blown embedded system, right? So the point, just to sort of recap where we went with all of this, was modern embedded systems are very rarely a question of pure hardware where you just design digital logic and everything works from scratch, or pure software where all you are doing is writing C code. You have a combination of both. You need to be aware of the hardware side of things. You bring in the notion of registers as one way by which software can communicate with hardware. You then bring in APIs and drivers, which basically say, okay, rather than directly poking registers, let me give some more meaningful functions that can be called by either the OS or by the applications that are using these drivers. And then finally, of course, on top of all that, you need to have something that can actually create the applications that run on these systems, right? So this course was sort of focused more on, from the digital side all the way up to at least the basics of drivers and how they interact with the kernel. As you would have seen, right, we have not done a deep dive into how an OS works. There are many aspects that we did not even touch upon, right? We just not really looked at resource management, scheduling, and so on, right? In fact, at best, all that you can say is you know a little bit of the surface of how an OS works, just sufficient to sort of understand how device drivers can interact with hardware. At the same time, we have also looked at how the hardware itself could be written in a way that sort of makes it meaningful and friendly to writing actual good device drivers. So that was sort of the focus of this entire course. Now, where do you go from here, right? Clearly this is just sort of a starting point, right? It sort of hopefully has given you a little bit of a flavor of the kind of things that are useful in building modern embedded systems. There are a number of other essential resources, Linux device drivers. This book, which is, as I mentioned earlier, it's actually deals with a relatively older version of the kernel, but most of the material there has actually not changed very significantly, right? So the ideas behind it still remain the same. There are other things mostly online, right? Very rarely would I say that this is a definitive book, go buy it. At this point in time, the most up-to-date information is going to be the kernel source code itself, right? So at some point you need to get used to the idea that going to the actual kernel documentation and reading the source code is probably the best way of understanding what's really happening behind the scenes. There are some nice websites and organizations that do provide useful information. Like I said, there are a number of advanced topics that we just touched upon. So even something like real-time Linux and how you can test latencies and so on is something that I just touched upon. The entire notion of high-speed buses like PCIe and so on was not covered at all over here. Partial reconfiguration, the build systems for Linux kernels. Once again, things that are useful and important to know, but not really within the scope of what we covered over here. What about alternative platforms? There are many variants. We've mostly looked at the basic Zinc, ARM plus PL. The UltraScale and the MP SoC, the multiprocessor systems on chip, are variants of that, very similar in behavior to the basic Zinc systems, but with more advanced features. Intel has their own variations on this. Well, now it's Altera, right? So Intel has again sort of split off. So Altera is the FPGA wing of things, and you also have a number of other companies that have RISC-V and FPGA combinations that they are bringing in. So it's not that this is entirely just the Xilinx Zinc platform. That was what we used in order to explain the usage that we are going through. And of course, at the end of the day, if you are really getting deeper into this, you need to get a deeper understanding of the community around this, a number of kernel mailing lists, Xilinx forums, and so on, that where you can basically find useful information online. So hopefully, this has given a clearer picture of the fact that if you combine the power of Linux as an operating system with the flexibility of FPGAs in terms of building custom hardware, you can get powerful embedded systems, right? And the only way to really continue learning over here is go dig deeper into the kernel source, play around with experiments, hardware, software, build projects, and hopefully, you get a good learning experience out of all of this.